strong AI relies on the assumption that intelligence can be reduced to a finite set of local, rule-governed steps. It treats cognition as a procedure that can be explicitly written down and executed without external intuition. Alan Turing formalized this standard in 1936. He defined computation strictly as anything calculable by finite means, a procedure so explicit it requires no human insight to complete. Turing's analysis began with the human computers of his era, people manually following strict step-by-step mathematical rules. He isolated the pure mechanics of their work to determine what a machine could, in principle, replicate. But in defining the boundaries of mechanical execution, Turing also discovered its absolute mathematical ceiling. The halting problem proves that no finite set of rules can evaluate all possible computational outcomes. Well-defined mathematical problems exist that a closed system simply cannot solve from within. Any system restricted entirely to a fixed set of procedures structurally guarantees the existence of uncomputable blind spots. This makes a perfectly closed, entirely self-sufficient intelligent system a mathematical impossibility. Despite these limits, modern artificial intelligence continues to absorb complex tasks once thought to require deep human cognition. Large language models process, translate, and synthesize information at a scale that challenges the idea of a rigid boundary. This tension is often framed by John Searle's Chinese room argument, which claims that a system following rules to manipulate symbols lacks true understanding. In terms of computability theory, this suggests that no fixed mechanized procedure can encompass the full scope of intelligence. We are left with a profound contradiction. AI systems are successfully encroaching on complex cognitive tasks while remaining strictly bound by the limits of formal procedure. Resolving this profound contradiction requires analyzing intelligence as an open-ended limiting process rather than a fixed or static state. When a cognitive task is mechanized, the work of specifying and correcting that mechanization reappears at a higher, non-mechanized layer. The labor of guiding the system is displaced upward. Understanding the trajectory of AI requires modeling the dynamic relationship between these stacked layers of computation as they are continuously extended. We start at the foundation of standard computing. In Turing's theory, this is the empty oracle. The machine relies solely on its internal instructions, receiving no outside information. This base state establishes a specific computational layer. Formally, a layer consists of all the decision problems a machine can solve relative to a given set of information, an oracle. Inside this layer, the system is strictly bounded by local closure. Any finitely trapped within the boundaries of its established current layer. The glowing boundary represents everything the machine can solve. Outside lies an unreachable node. This is the Turing jump, the precise halting problem representing processes the machine cannot confirm will ever finish executing. Scaling up hardware or data will not bridge this gap. The boundary is structural, meaning the system is mathematically locked out of solving its own jump. Progress in AI does not occur by making a direct, instantaneous leap from a base layer to its absolute boundary. You cannot simply program the Turing jump. Instead, computing advances through step mechanization. This involves navigating upward by finding intermediate mathematical footholds, new oracles that are stronger than the base layer, but fall short of the absolute limit. This progression is governed by a strict mathematical inequality. The new layer, B, is strictly greater than the base layer A, but strictly less than the Turing jump, A'. Between the baseline and its open boundary, a new intermediate node is established, providing new capabilities. By securing this step, the system mechanizes previously unsolvable problems. Instantly, this new baseline generates an even higher relative boundary. Each successful mechanization formalizes a new baseline and pushes the theoretical frontier further out. Some assume that massive internal feedback loops and iterative self-play are sufficient to trigger general intelligence. Computability theory shows that if a system updates its own parameters via a computable rule over any finite number of steps, it remains entirely trapped within its original degree of computability. Internal repetition produces localized refinement, not structural ascent. Genuine ascent to a higher mathematical layer requires shifting from finite iteration to limit computation. The left panel shows finite internal updating, looping in place. The right shows a one-level stable revision, an approximation revised over time until it stabilizes into a permanent limit. This stabilized outcome mathematically equals the Turing jump layer. This movement beyond fixed rules requires a higher order capacity for ongoing evaluation, meta-level correction, and stabilization. If stable revision can reach the first boundary, we must ask what happens when that revision process itself is formalized and absorbed into the system. This leads to two-level nested stable revision. The system calculates an inner limit to stabilize its variables and then applies a secondary, outer limit to stabilize the rules governing that first process. Theorem 5 proves that the outcome of a two-level nested revision matches the second Turing jump. It is a full mathematical leap above the first boundary. This pattern projects outward as a progressive oracle sequence, a historical chain of strictly ascending layers, each defined by increasingly complex, deeply nested revisions. A system's position on this infinite ascending scale is determined by the depth of its capacity to revise its own rules. This abstract mathematical tower is reflected in modern software engineering. We can see the structure and how current language models are built and deployed. The settled weights of a pre-trained language model represent the base execution layer. The model applies fixed statistical rules to generate an output. The surrounding architecture pushes capability higher. The middle tier represents intermediate automation, code generation, and agentic prompting, correcting the base model's output. The top tier, meta-level reframing, is occupied by human engineers, acting as the external oracle. They set objectives and force revision when tools fail. Current AI systems do not operate without an oracle. Human intelligence provides the higher-order jump functions required to pull mechanized layers upward. Metatasks currently performed by humans, like evaluating prompt effectiveness and setting objectives, will eventually be successfully automated. This automation creates a new baseline computational layer, which immediately pushes the requirement for new guidance even higher up the chain. This leads to the whole process oracle, representing the infinite join of all historical stages of progression, every baseline, jump, and revision. The whole process non-capture proposition proves that no finite oracle stage can ever compute or contain the entirety of this historical progression. The complete chain always exceeds any single link within it. This proof demonstrates that intelligence is the open-ended pressure that breaks through local closures. It is the mathematically mandatory process of establishing stronger rules the moment existing procedures cease to suffice.